Alright guys, we're moving on to chapter 2, but before we do, I want to revisit one of the ideas from chapter 1. They mentioned a couple of times sentinel values, and so I want us to write a little program that actually uses a sentinel value. A sentinel value is just a value that means stop. Please enter your score, or -1 to quit, that kind of thing. So we're going to write a program that does that kind of thing. It's just going to add up a series of numbers. I'm going to do the pseudocode for it first. You don't have to write the pseudocode down. Set total to 0, set number to 0, while, I forgot my start and stop block if I was going to make it proper book ready pseudocode. While number is not equal to -1. Input number, if number not equal to -1, add that number. Total plus equals number. Now, total equals total plus number. Or we could, rather than expressing it as an algebraic phrase, we could just say add number to total. Just as good. And then output, the total is, comma, total. That's our pseudocode. Obviously, it's not programming language, but we'll make it in the programming language pretty easily. So what the word while does is it sets up a loop. If this condition here is true, it goes into the loop. And then when it's at the bottom of the loop, when it finds the first unindented instruction, it goes back and it checks to see if that condition is true. And if it's still true, it repeats the loop. And it keeps repeating until this condition becomes false. So we've set our condition to be not equal to -1. So as long as they type in something that's not equal to -1, it's going to keep looping. So we're going to ask for the number. If the number is not equal to -1, we're going to add that number to total. And it's going to come back up here and check again. Is the number not equal to -1? It sure is. So input the number, add it to the total. But finally, when we get here and they did type in -1, then it's not going to do the add number to total. And then when it loops back up here, this is no longer true because the number is equal to -1, and so it bails out of it. So that's a loop. When you write a loop, you need to make sure that there's some way to exit it. There's usually two ways of exiting a loop, but one is for this condition to become false. And if that condition never became false, it would keep running forever. That's known as an infinite loop. Usually you want to avoid infinite loops. Usually you want some way for the program to exit. So that's our pseudocode. Let's go ahead and do it in Python, and then we'll do it in a flowchart. We could do it in the opposite way. I mean, really you should do your flowchart before you write your program just to get the logic in your brain. But let's go ahead and do it in idle. It is recorded. Thank you. All right, yesterday I had a whole bunch of people type code into this place. You don't want to do that because if you made a single mistake, you couldn't correct it and you'd have to type it in from top to bottom. So always do file new once you load Python. And I know y'all already know that, but had a couple people who have bit them yesterday. All right, so I'm just going to call this one February 7 because I'm not creative. Here we go. So I'm kind of just getting my pseudocode to the side there, since my text is larger than yours. Alrighty, so do we need this start command in this language? No, but I am going to put my name up at the top. Please always do that, the date, and a description of what the program is, even if it's just daily notes. Or, you know, assignment 2 or whatever. Alrighty, I am going to put the start command as a comment, just so that I have a line-by-line transcription, but it's not really there. Alright, set total to 0. Alrighty. Total equals 0. Set number to 0. Okay. Number equals 0. While, and we're not going to write it out like this, not equal to -1. Instead, we're going to express it in grammar. While number not equal to -1. That's an exclamation mark, exclamation point. That's an equal sign, and don't put a space between them. Colon. And then once we hit the colon, the next line should be indented. Okay, and then it says input number, but if you remember from Monday, what we said is that whenever you see input on pseudocode, it's usually going to take several steps over in Python. You have to print a message, you have to get the number, and then you have to convert it. You can kind of combine two of those steps. You can kind of combine the print and the input into one step, so I'm going to do that this time. Number is equal to input, and then I'm going to put a message inside the input statement.
Quick question.
Yes, sir.
What is it? Exclamation point mean?
It means, pronounce it as not equal. Otherwise, if we were checking to see if it was equal, we would use two equal signs. Good question. So number is equal to input. It means you're thinking about it and not just typing. So number is equal to input. Enter a number to add, or -1 to stop. Of course, this means that you won't be able to add -1 to your numbers, but all right, just an example. So now we have that number, we need to convert it to a number. Anytime you have an input statement, if you're talking about numbers and not names or other strings, you have to convert it to a number. So number is equal to float number. Turn this number into a floating point number. Why did we use float rather than int? Because ints are for whole numbers only. And it would crash if you typed in 3.5 and we tried to convert it to an int. Now we have that number. What's the next on our pseudocode? If number not equal to, so it's going to have that same syntax with the exclamation point. If number not equal -1 colon, add number to total. Alrighty. Number equals number plus total. No, wait. We're not adding the total to the number. We're adding the number to the total. Total is equal to total plus number. And I'm going to show you an alternate syntax underneath that I actually prefer. I'll start switching towards it, but I'm just putting it as a comment. Total plus equals number. What that means is take that number, add it to total, and store it into total. Just like this. It's just a shorter way of writing it. I kind of prefer it, but I don't care which one you use as long as you recognize what I would mean if I typed that. Okay, so next, we're done with the if statement, so we need to back up one. We're done with the while loop, so we need to back up another. And then for my output, I'm going to do print. The total is, comma, or end quote, comma, total. I'm tired of that start being up there. I'm going to remove that start comment. So I'm going to save it with Control S, and then I'm going to run it. See if I made any syntax errors. It says please add a number or -1 to stop. 10, 20, 30, 40, 50, -1. So it ran until we typed in a -1. -1 being the sentinel value, the value that told it to stop. If you were writing this program for your own use, are there any changes you would make? I'm kind of thinking of one in particular. But as I'm adding these numbers, would it be nice to see any additional information? Like if you were using an adding machine, or if you were using a calculator, what would you hope to see as you added your numbers together? Yeah, you'd want to see a running total. We could do that. Easiest way to do that would just be to copy this line here and paste it up there, but I'm not going to be that lazy. Let's so here I want it inside the if statement, the body of the if statement. So I'm going to make sure that it's indented properly, so it's lined up under that one. Print current total, print parentheses quote, current total is in quote, comma, total. That way we can just watch that value increase as we go on. I'm not sure if that improves the appearance or not, but it's useful information. And a -1 to stop. All right. So we've written a program using a loop, a while loop. I may skip flowcharting that for now. I'm eager to get on to the second chapter. But I want to make sure that everybody got this up and running. So I was just reminded that we almost have a superfluous print here. And what I mean is, we're going to mess with this just a little bit. I'm going to delete that line, that one line that says print current total is. I'm going to delete that one. Remember, to delete a whole line, I just hit shift down arrow. You can always use your mouse, and then the delete key. And then I'm going to tab this print statement over. But just because I like to see something at the very end of the program, I'm going to put a print done. So now when it runs, it's going to do about the same thing as it did before. Now why is that? Because if I can get 2 copies of this going now. I'll bring it back just a second for those of y'all typing along. Okay. All right, so if we line these up before and after the changes we just made, this was the version that we had before I started walking around. No, this is the version we had before I started walking around, and this is the modification to it. So if I took this done message out, we'd see how similar they are, but the difference is. What we did is we took this print statement out from underneath the if. And then we moved this print statement so that it was part of the while loop, so that it would happen every single time. Because that was the goal of this one, was to happen every single time. And so, by moving it there so that it's not conditionally based on the if, but it is part of the while loop, we didn't really need to print a running, we didn't need to have a second print message down underneath. So maybe that's a slightly more organized approach to it. Both of them would be totally good solutions for the problem. And our pseudocode didn't mention anything about printing a running total, so if we turned in a program that didn't have that print statement there, that would be fine as well. But that's quite often the case, is that you will be working from pseudocode and then you will embellish it to make it a good program. The pseudocode is basically just the logic. It's kind of the framework upon which you're going to build your code. All right. Put my done back there. Or instead of a done, I could do this. Input, press, enter to finish. Something like that. That way, if you double-clicked it from the Windows interface rather than running it from within idle, you'd actually get to see the output. All right. That's what happens if you run it and you type in some non-numeric input. You get a crash. It says value error, could not convert string to float. Is that a syntax error? No, it's not a syntax error. It's because we gave it bad input. We will learn how to handle a bad input at a later point. All right, elements of high-quality programs. In this chapter, we will learn about declaring and using variables and constants. Constants are a great idea. Python doesn't have them, but you can simulate them. Performing arithmetic operations. We've kind of already been doing that. We've been doing addition and multiplication. Modularizing a program, hierarchy charts, features of good program design. Declaring and using variables and constants. So, understanding data types. The type describes what data can be held by the item and how the item is stored in memory. What operations can be performed on the item. You can't do math on a string. Like if you type in your name and then you say x is equal to name divided by 2, what is this supposed to do? Now, oddly enough, you can do multiplication with strings in this language. It's kind of a quirk. Let me show you that. I'm going to load up idle again. I did not mean to close it completely. Alrighty, so go do run Python shell. And then do this. A is equal to, and type in your name. Now do print A plus A. Now print 10 times A. So it kind of looks like we're doing math with strings, right? A is a string because it's containing that string named Bob. When we add two strings together, that's called concatenation. Fancy word for adding two strings together. Kind of like appending. That appends a string to itself, so we see our name twice. And then this is the really weird one. The multiplication in Python means concatenate the string to itself 10 times. So we see our name repeated 10 times.
So it's called concatenate?
Yes. Let's spell it out. I'm just going to actually type that into my program. I'm going to delete that input, enter to finish line now that we're adding stuff to it. But A is equal to Bob, and then print A plus A, and then print A times 10. And add a comment. Appending strings together is known as concatenation. But other than the plus symbol and the multiply symbol, you can't do math with a string. You always have to convert it to a number first, which is why we do that command. So typically, programming languages will hold numeric data types and strings. Numbers are the stuff that you can do math with. Strings are everything else. Names and addresses and things like that. All right. I'm going to totally skip the slide on constants. No, I better not. What if there's a quiz question online about it? This code here has one constant. Actually, it has three constants. That's a constant, that's a constant, that's a constant. But I'm going to talk about that one in particular. Why is that a constant? Well, because nothing will ever change it until you go in and you actually edit your program. That number is one that the user doesn't edit. It's one that you edited when you made the program. And so it's an unchanging number. Now that's kind of abstract for a constant, but you know, one that people are more familiar with would be pi. And so you could do this. Pi is equal to 3.14159. And then if you wanted to figure out the area of a circle, you know, you could do radius equals input, quote, what is the radius, end quote, in parentheses, and then we could calculate, well, we have to convert it to a floating point number. Radius is equal to float radius. But now let's get the circumference of that circle. Circumference is equal to 2 pi r. So 2 times pi times radius. And then we may as well print that out since we calculated it. The circumference is, I usually do area because it's easier to type the word area than circumference. The circumference is end quote, comma, circ. That's what I called my circumference variable. Just make sure I don't have any syntax errors. Radius is 10, so the circumference is 62. Okay. So, in other languages, you would mark that variable pi as being a constant by preceding it with a word like const or final, depending on the language. This language does not support that. But you can indicate that you may mean for it to be a constant just by putting it in all uppercase letters. That is a convention. Name constants in uppercase letters. So why would you bother sticking 3.14159 in a constant rather than just putting it in the equation itself? Don't make this change. I'm going to undo it immediately. Couple of reasons. One is that not every number is as recognizable as 3.14159. You know, that just happens to be the most famous mathematical constant. And so it could be other numbers. You know, the speed of light is 6.0 times 10, whatever, you know. Or, you know, the gravitational constant, Planck's constant, the BMI ratio for calculating weight against height, whatever, you know. If you make these things constants and you use variable names to support them, the equations are easier to read. Also, what if we used pi 17 times in this program, but we mistyped it one time? You know, one time we had 3.13159. Well, you might not notice that bug, but then your Mars lander crashes into the planet because you typed it in wrong one time. And that sounds silly, but I'll give you all the reason why I said that in just a minute. So, by making things a constant, you make it so that you only have to change it in one place if it ever updates. So we could use that value 17,000 times in this program, but we would only have to change it once. And there would be no mistaking, you know, no typo in using that number over and over and over. So that's the idea of a constant. This number right here is what's known as a literal constant because it doesn't even have a name, right? It's not -1. I mean, you know, it's not pi or whatever. It's just a number. So is that one. That's just a number. That one's a number. Those are known as literal constants. And so if you hear me say the word literal, that's what I mean. I mean something that's typed in directly into the program. not entered by the user. Bob, that's a literal because it's typed into the program itself, right? You added that text, or you put your own name in there, whatever. This is a string literal. The user certainly didn't pick that, I did. So is that. So all of the numbers we see and all of the strings we see are literals. These are numeric literals, and these are string literals. But they're a form of constants. And like I said, other languages let you define constants by putting a word in front of them. And the advantage to that, like I said, don't type this because I'm going to erase it, is that if I was able to define pi as a constant, then later on, if I made a mistake and tried to set it equal to something else, the compiler would say, no, you can't do that. That's not a legal operation. You said that this value was never going to change, and so I'm not going to let you change it. But Python doesn't have that word. We'll erase it. I talk about what other languages do, both because you're going to probably go on and use other languages other than Python, and also the book sure does talk about them. So, a string constant contains alphanumeric values. Alphanumeric meaning letters and numbers, but it can be more than that too, right? It can be all the punctuation, the question marks and periods and stuff like that. Can contain both alphabetic characters and numbers. Strings are enclosed in quotation marks. What are variables? Variables are named memory locations. They have a type, they have a name, and a value. So in their flowcharts, it looks like they want us to declare our variables before we use them. In Python, you don't have to do that. In C++ and Java, you do have to do that. You have to define your variables before you can use them. In one case, we did in our code. Let me show you. We did sort of define our variables before we used them. So it's not a totally bad idea, right? We define that variable and we define that variable. Why did we do that? Because we couldn't check. We couldn't use a while on a variable that had never even been created. So we had to have it there. And why did we create that variable? Why did we declare that variable? Because we wouldn't be able to add anything to it if it didn't exist. So according to the flowchart, these are declarations. Seems like I have two simultaneous files going. Let me close one of them. Alrighty. So going back up here, these are declarations. We're declaring our variables. Declaring a variable is just when you give it a name and you put in a starting value in it. In other languages, declaring your variables can be a more complex thing, but for Python, that's how you do it. Declarations. Declare our variables. That's another variable declaration right there. Here's another variable declaration. We are declaring the circumference variable and storing a value in it. So for types, a numeric variable can hold digits, and we've broken our types down into two different. We have integers, which are whole numbers, and then we have floating points, which are have decimals in them, 3.4. That kind of thing. And then a string variable can hold letters of the text or punctuation or numbers. Type safety prevents assigning values of an incorrect data type. Well, our language doesn't do that. I'll tell you what that means, and then you can kind of toss it away for now and then remember it the next time you take a programming course. If I had done this, if I had done A is equal to Bob, which I did up there, in those languages, I would first have to declare what kind of data that was. I'd say, okay, this is a string. And once I declared it as a string, I couldn't do anything else except store other strings in it. I could turn around and change it to something else, like that. That works, but if I did this, A is equal to 3, that would give me a syntax error in those languages. Now, Python doesn't care. It's happy to go ahead and store 3 in there as soon as you had a name in there. It just changes the data types on the fly. But the book says that you can't change the data types, and it's not a bad idea. The only place that I change the data types in a Python program is when I get string input and I immediately turn it into a number. To me, that's legal in this language. So you're not supposed to reuse the same variable name to hold different data types. If you have something called name and you have stored, George in it, don't turn around and store George's salary in it, right? I mean, that's kind of obvious, but, $12.95 an hour, whatever, Don't reuse the same variable name to hold different data types. I would call that one wage rather than name, something like that. So the identifier is a variable's name. You get to choose the name. You should choose reasonable and descriptive names. Now when I'm up here coding and I'm just trying to give you a pure, simple example of something, I may use a single letter for my variable name, like I did here, right? I just said A is equal to Bob. Why? Because that was the easiest thing to type when I wanted you to do A plus A. I didn't want you to have to type in name plus name, right? That was like four times as fast to do it that way. But in real code, you want to give your variables good names. Total, that's a pretty good name. It indicates what it's going to hold. Number, that's also a pretty good name. The program would work just as well if that variable was called Fred, right? Or if I just made it F, or if I made it F1. And this program would work just as well if instead of number, I had this one called, P93. All right, there we go. Now that's stupid, right? I mean, looking at it, it doesn't make any sense. And it's kind of an extreme example. But if you give your variables good names, it makes the program easier to understand. And you should write your code in such a way as it's easier to understand. Because you write your code once, and then in an environment where code is maintained, it's read many, many, many times. So it's more important for the code to be easy to be read than it is for it to be written. So the variable names are just for our purpose. The computer doesn't care whether I called that Fred or whatever. But we care, because that obscures the meaning of what it's trying to do. Looking at this code, it would take a little while to figure out, oh, what is it doing? Why is the total Fred? It throws some confusion in. The same thing just applies to single letter variable names. They're so easy to type that they're seductive. I could have used T for total and N for number. Yeah, you just have to kind of balance it. Is it easy to read? Is it easy to understand? If T really was easiest to understand, you could do that. Usually you want something more than single letter variable names. The exception for that in my mind are loop variable counters, which we'll talk about at a later point. So programming languages have rules for the identifiers. They can have letters and digits. They can be upper and lower case. Some languages allow hyphens. I do not believe that to be the case, because a hyphen here is just a subtraction symbol. So in our language here, what are our rules for variables? Variable names can be letters or digits or underscores. And they have to start with a letter. And that's very similar to a lot of languages. These rules are common. They're not just Python quirks. They're the same in C, C++, Java, a whole bunch of other languages.
Scroll up just a little.
Yeah, sure. What part are we trying to see?
The last 2 lines.
Oh, like that?
Yeah.
Okay, sorry. So that means that some variable names are illegal. If I did this, tax rate to 2018, that's a perfectly good variable name. It's made out of letters and digits. And it started with a letter. But if I did this, 2018 taxes, this is a good variable name, and this is a syntax error because it started with a number. Now when naming things, some people do them like this. Patient underscore height. And then some people do it like this. Patient and with a capital H, height. Both of those are good ways to name a variable. You just pick the one that's easier to read. This used to be a very popular way of doing it. Most of the world has kind of progressed to doing it this way. So these are both good variable names. You get to pick which kind you want. You want underscores? Great. If you want to put capital letters in them to make them easier to read, great. However, there are some words that you can't use as your variable names. Generally, they're anything that shows up as blue or orange or purple on our programming language. Anything other than black is a very bad variable name. Right? If I did this, print is equal to 3. Don't type that because it doesn't work. That's great and all, but then I'll never be able to print anything ever again. You know, if I tried to do this, if I tried to print hello, that'd now be a syntax error because I assigned a value to the print function. I wiped the print function out. A lot of other languages wouldn't even let it compile. This one will. But that is a built-in function, and we don't want to replace the built-in function. We don't want to treat it like it's a variable. Okay, now all languages would refuse to do this. While is equal to 3. Or if is equal to 7, 8. Or def. Nah, I'm going to skip that. Anyways, why? Because these are keywords. These are words that are reserved. The language depends upon these words as part of its grammar, just like we saw up here, while and if. So you can't redefine those words at all. These two lines would be a syntax error right there. So I'm just going to put a comment down here. Variable names cannot be reserved keywords or function names like print, sum. And basically the way you know if it's a special word is if you're typing along and it changes it from a color other than black, you know immediately it's not a good variable name. Now I love the variable name sum, 3 letters long, but sum is a function, so I can't use it. That's why I use total rather than sum. There are other built-in functions like max and min. You see those changing color as I type them? That means that those are functions. Like what if we did this? A is equal to the maximum of 2 values, 10 or 20. At that point, A is equal to 20 because it picked the maximum. So max is a function. It evaluated those 2 numbers and then returned the larger of the 2 to store into the A variable. So max is a built-in function. One book thought it would be cute to call them BIFs for built-in functions. Yeah, whatever. Okay. There are other ones like that. There's sum, there's min, and int when we do that, right? Or float, those are built-in functions. Print is a built-in function. Everything up here that was in purple is a built-in function. Input. Those are different than keywords, but the idea is very similar. If the language gives you these built-in functions, you're probably going to want to use them rather than erase those functions by treating them as variable names. So our reserved keywords are things like if, while. I think those are the only ones we saw here, the only words that are in orange, but there's more of them. Variable names are case sensitive. And so when I'm walking around helping people, the syntax errors that I see most often are people will do something like this. You don't have to type this because it's a syntax error. Name is equal to Bob, print name, right? Looks good, you know, why not? We start our English sentences with a capital letter, but this has to exactly match that. And so you just need to either make that a capital N or that a lowercase n. The other mistake that people make, you know, is just typos, you know, or, you know, adding an S to one variable and not to the other, whatever. So variables are case sensitive. Name is different than name. And if you are a very, very, very bad person, you can deliberately mess with people by interchanging the L and the lowercase L and 1 in your variable names, like total, and then end it with a 1 rather than an L. Yeah, and then when somebody else is trying to modify your code and it kept breaking, they wouldn't know why. Don't do that. Try to pick variable names that are easy to understand and that don't mix things up like that. Another one to be concerned about is capital O's as opposed to zeros. Usually that's not a problem, but if you name something that has a capital O in it, don't create another variable name that has a capital 0 in about the same place, right? So just be concerned that lowercase l's look like 1s and uppercase O's look like 0s. It's part of picking good variable names. They should have some appropriate meaning. They must be one word, meaning no spaces. You can't say my space age is equal to 3. Or your space age equals 7. You know, right? That space would cause a syntax error. Variable names must be one word, must start with a letter, and should have some appropriate meaning. So if we were going to make rules about variable names and type them all out, I'm going to start a quote in my code here so that I don't have to keep putting a comment like that. I'm going to start it off with 3 quote symbols, 3 double quotes. So variable names, to sum up our rules: letters, digits, underscores must start with a letter, cannot be a keyword, should not be a function name, are case sensitive, should be meaningful. One letter variable names are bad. And again, I just use them up here because sometimes it's easiest to type. And when everybody's typing along with me, I'd rather reduce the number of syntax errors we get. Now I'm going to end that with 3 more quotes. This is a way of blocking off an entire section of code, is to use the triple quote thing. So the next thing I type is actually going to be valid code. If you need to indent a whole bunch of code at one time, like say that I wrote this and then I realized that it should have all been indented, I could highlight it all and then go to Format, Indent. Format, Indent. And then if I needed to shift it all back the other way, I could highlight it all and do Format. I would have called it unindent, but they call it dedent. And there are some other options up there too. There's one called comment out region. So if there was a set of code in here that I didn't need anymore, I could highlight it all and choose comment out. And it would put those, you know, hashtags in front of it. I'm going to undo that. No reason to have that code commented out. So variable naming conventions. Some people do this. Variable name with a hump in the middle. Hump in the middle being a capital letter. Pascal casing. This is kind of a who cares, but some people put the first letter of the variable name as an uppercase letter. And then Hungarian notation is where you actually put the data type as part of the variable name. This has kind of fallen by the wayside. It was invented by Microsoft. I just recommend either using camel casing or using underscores. One of the two. Yeah. Snake casing. They had to give it a great name, huh? Snake casing is when you use underscores. And then mixed case with underscores. And then kebab case. I like that. Kebab case where you separate them by dashes. But that doesn't even work in our language. So to assign a value to a variable, and in pseudocode it's done like that. Set my answer equals to whatever. But in a programming language you leave the word set off. That equal sign is known as the assignment operator, just like the star is known as the multiplication operator. It's a so-called binary operator, not because it's made of zeros and ones, but because it has two operands, meaning it's got two things on either side of it. The equal sign, well, for example, the multiplication sign. How does multiplication work if you're not multiplying two values together? So that's your operator, that's your operand, or those are your operands. Similarly, the equal sign has two operands. One side is the expression, the entirety of the expression, and the other is the variable in which it's being stored. So, now we're going to start throwing in some really programmery terms. This has got right associativity, just meaning it goes from right to left. This value is calculated, and then from the right side it gets copied into the left side, which is the variable. The result of the left is called an L value. Alrighty. Yeah, so that's the left-hand side, L value. Am I ever going to use that term again? No. If it shows up in an exam, it's not my fault. I'm not going to put it in an exam myself. Initializing a variable. Initializing a variable is when you give it its first value. And these examples are not drawn from Python, where you would have to declare your salary as a number or your name as a string. In Python, you just do that. Your name is that, or your salary is that. Garbage is a variable with an unknown value. Python doesn't have garbage variables, but other ones do. I'll show you an example of what those would look like in those languages. I'm not going to type them into my code. You shouldn't either. So, in those languages where you have to predefine your variables, you have to declare them before you could use them, you could do this. Int number, int total, number is equal to 3, total equals total plus number. Now there's a problem here. What is wrong with this code? Conceptually, what is wrong with it? We can't even type it into Python to figure it out, but how could we add 3 to total if total didn't have a value, right? So if total doesn't have a value, you can't increase it by 3. The computer doesn't know what total is equal to. So it's got a so-called garbage value. It's undefined, it's undeclared. It has not been initialized. Python doesn't have garbage values. We don't have to worry about that because the act of declaring a variable in Python is the same thing as initializing it. So here we declared and initialized our circumference variable or our pi variable. So variables must be declared before they can be used. That's a good point. How could you print total out if you had never created total to begin with? A named constant, it's similar to a variable. You assign it only once. Give it a good name. And treat it as a value that will be never changed during the program's execution. And the way that you signal that it is a constant is that you put it in all uppercase letters. And that tells you that you shouldn't change it. As I mentioned, in this language, you do not have a constant keyword to force that variable to be the same throughout the program. So it's just kind of like a gentleman's agreement. If something is in all caps, you don't change it. You just use the value that was given. All right, arithmetic, plus, minus, times, division. The plus sign, the minus sign, the asterisk, and the slash. We know what those mean. We just have to be concerned a little bit about the order of operation, in what order things are done. So if I do this, 1 plus 2 times 3, which happens first, the addition or the multiplication? Yeah, according to your order of operations from junior high or whatever, multiplication happens before addition. Now, if you just punch that into a simple $5 calculator, 1 plus 2 times 3, it wouldn't do order of operation. A more expensive calculator would. So, this is actually equal to, that happens first, which is 6. And then you add 1 to it, it becomes 7. So that's equal to 7. How about 1 times 2 plus 3? What happens first now? Yeah, the multiplication happens first, because it always happens first before division, so that's just 2 plus 3, and that's 5. So our order of operations, the good old acronym or mnemonic PEMDAS. Please excuse my dear Aunt Sally. I didn't make it up. P are the parentheses. E stands for exponent, which in this language is not represented by the caret. It's represented by 2 stars. And then you have MD, which stands for multiplication and division. Which is either a single star, or a divide by. And then you have AS, which stands for add and subtract. And these work as categories. So inside this category, multiplication doesn't have priority over division. Division doesn't have priority over multiplication. You just do them left and right. So it's not like if you saw this phrase, don't type, I can't tell you what to type or not, but if you saw this phrase, I'm trying to craft this in such a way that it actually means something. Alrighty. So if you saw that, and then you looked and you were trying to go by PEMDAS, and you said, well, I have to do multiplications before division, so I'm going to do that one first, that gets you the wrong answer. Multiplications and divisions are the same priority, so you just do them left to right. So what's 12 divided by 2? It's 6. Times 3 is 18. Addition and subtraction work the same way. You don't go through the entire expression looking for the plus signs and then looking for the minus signs. So if you had this expression, B is equal to 6 minus 2 plus 3. Something like that. You wouldn't go, okay, I better do addition first. So 6 minus 10 is negative 4. Instead, you just do them left to right because they're all the same priority. But you do have to care very much about these order of precedence that way. You use the parentheses to force the order of precedence to change. So if we had this, A is equal to 1 plus 2 times 3, and you wanted the 1 plus 2 to happen first rather than the multiplication, which it would do by these rules, you just put parentheses around it. Like that. And I know that vast majority of us are already familiar with these concepts from earlier math classes. We're just kind of talking about them at a programmerese level. Any other comments I need to make about that? don't think so, but I'm going to set up a few of these. If you just kind of, they're going to be small ones, so you ought to be able to figure them out in your head. So you might just, write them down, put them on pencil, whatever, or we can work on them together. So if we have 1 plus divided by 3 minus 2, or we have 2 times 3 plus 6 divided by 3. We have 2 times 1 plus 2 divided by 4. Alrighty, go ahead and solve those 3 expressions. You can do them in your head, great. But don't whip out a calculator and punch them in. So what's this first one? What's that equal to?
1.
Yeah. Why? Because 6 divided by 3 is 2. And so then we do 1 plus 2 minus 2. I typed in 2 there. I meant to type 1. If I fingered it. How about that one? So we have 6 plus 2 is 8. Did I do that one wrong? So 6 divided by 3 is 2. 2 times 3 is 6, so that's 8. And here, what is that equal to?
1.
1 again. Because 1 plus 2 is 3. No, it's not. Wait. Alrighty, so what's 1 plus 2? That is 3, so 2 times 3 is 6. No, 2 times 3 is 6. Divided by 4, I didn't mean to make it where it didn't work out totally, but whatever 6 divided by 4 is, which I guess is 1.5. If I'd been planning ahead more carefully, I would have made it divided by 3, so that when we did 6. So 1 plus 2 is 3, times 2 is 6, divided by 3 would be 2. All right, does that make sense, guys? If I gave y'all, sheet of paper as a pop quiz with about 5 of those expressions, you'd be able to do them? Hope so. If you're ever in doubt, or if you think it'd make it easier to read, go ahead and use parentheses. Using parentheses even where not strictly necessary is not a bad thing. So like if you have this expression, A is equal to B plus C times D to the power of 2. We didn't do exponents, but remember, exponents happened before multiplication and division. And if you felt like making it easier to read, you could do that, even though it wasn't necessary. Those parentheses are not necessary because those exponents are the highest priority thing in the equation, so they would get done first anyways. But you can use parentheses to make it easier to read, or to change the order in which they are evaluated. Like if you really wanted B plus C to be the first part of it to be done, then you would put that, in parentheses. Okay, so we know how to do math, parentheses, exponent, multiplication, division. So 3 to the power of 2, what is that? That means 3 times 3, which is 9. We know what 4 divided by 2 is, that's equal to 2. We know what 5 divided by 2 is, that's equal to 2.5. However, there's another operator besides this series. There's one called floor division. I'm going to write all the operators that we're going to talk about out again. Okay. So that's addition. That's subtract. That's multiplication. That's division. This is floor division, which means round down. 2 slashes means round down. Then this means modulus. And this is exponent. So the one that sometimes trips people up is modulus. But we'll get there. So if 5 divided by 2 is 2.5, then 5 divided by 2 rounded down is what? 2, right. So floor division just means do the division, then drop any fractional parts. So 6 divided by 2 is 3. 6 floor division 2 is still 3, right? We just lost a fractional part, but there wasn't any fractional part. So that's floor division. It just means give me a whole number as your answer. Round it down, please. Modulus means remainder. So if you have this 3 divided by 3, or floor division 3, that's 1 with a remainder of what? Nothing. If we have 4 floor division 3, that would still give us 1, but what was left behind? 1, right. People sometimes say 0.3, but there was a 1 left behind. 5 floor division 3 is 1 with a remainder of 5 divided by 3 is 1 with a remainder of 2. And then 6 divided by 3 is 2 with a remainder of 0. So 3 modulus 3 equals 0. Four modulus 3 is 1. It means 4 divided by 3, take the remainder. 5 modulus 3 is 2. 6 modulus 3 is equal to 3. No, it's not. What is 6 modulus 3? 0, right. So what if you have 8 divided by 10, or floor division 10? 8 floor division 10. What does that give you? What's 8 divided by 10 rounded down? It's 0.8, right, which rounds down to 0. And then what was our remainder? 8. Hope that makes sense. So 8 modulus 10 equals 8. 9 modulus 10 is equal to what? 9. And then 10 modulus 10 is what? Right. So that's the modulus, which means remainder. And exponents we're already familiar with. 3 to the power of 2 is 3 times 3, which is equal to 9. 10 to the power of 3 is equal to 10 times 10 times 10, which is equal to 1,000. Sorry, those are supposed to be double stars. I hate making mistakes. There we go. Like that. Oh, we are almost out of time.